Just briefly summarize what we did last time. We derived a formula to find the derivative of a logarithmic function on a base b. And then the special case when we have the logarithm base e, which is the ln. And that's the easiest case. Well, everything is summarized here in the definition box. And we also got the chance to do one example of finding derivatives of logarithmic functions. Well, so let's do one more example. So number one, okay, for the first example that we did last time, we worked with the natural log, which in this case it's only 1 over the expression inside parentheses times the derivative of that expression. Well, so when the logarithm it's a base other than the natural log, that is the base e, we have to use a different formula. It's right here. Let me copy it down just so we don't scroll up and down every time. So that's the derivative with respect x of log base b of u. This is 1 over ln of b multiplying the u times du with respect x. Essentially, it's a more generalized version of the formula using the chain rule for this. Well, how is that going to work for our exercise letter B? Well, number one, the derivative of log base 3 of sine x. Well, this is a composite function. It's composed by an outermost layer logarithmic function and an innermost layer sine of x. So, y prime, which is the derivative, is 1 over ln of the number that it's in the subscript, which in this case is the base of the logarithm. That's 1 over ln of 3 times the quantity u, but in this case the quantity u is the expression inside of the parentheses of the logarithmic function, which in this case is sine x. And then that times by chain rule the derivative with respect x of this sine x. Alright? So we're almost done doing the calculus, except that the only need to do here is follow this last instruction, which is the derivative operator on the sine function. And what's the derivative of sine? Cosine. So 1 over ln of 3 times sine of x and times cosine x, which equals cosine of x over ln of 3 sine x. Essentially, this is final answer. I think this is an acceptable answer. But if you wanted to simplify a bit further, you could use trigonometric identities. So let's see. Does anybody remember what's cosine over sine equals to? Is that a cotangent? Well, that would be a good simplified cotangent of x over the natural log of 3. And that's final answer. However, either answer is acceptable. Cosine over sine or its counterpart cotangent, or equivalent, not counterpart, equivalent cotangent. Alright. Let's go ahead and do one more exercise. So we have f of x equals to the square root of ln of x. So again, we have a composite function, in this case an outermost function, which is a radical function, and an innermost function, which is the natural log function. So, well, we cannot just differentiate the square root the way it is. We need to write it, or to rewrite it, rather, as ln of x raised to the 1/2 power. Alright, so we're going to use the chain rule in this one because we have a composite function. So f prime of x will be, okay, this 1/2 jumps to the front, parentheses, 1/2 minus 1, and have the ln x inside the way it is. And then multiply by the chain rule by the derivative with respect x of ln of x. Okay? So number one, what's 1/2 minus 1? It's a negative 1/2, so ln of x to the negative 1/2. And what's the derivative of ln x? It's just 1 over x, alright? Just 1 over x. That's the simplest case of the derivative of a logarithmic function. The one when the base of the logarithm is the base e. So what do we mean by base e if I don't see the e? Well, technically this ln x is the same as saying log base e of x. Just like we have log base 3, log base 10, log base your favorite number. In this case, ln of x is a special logarithm because it has the base e, which is the natural exponential or Euler's number. Well, let's go about the simplification of this. So number 1, I'm going to send this ln of x to the negative 1/2 to the denominator with positive exponent. That's ln of x to the 1/2 times 1 over x. And then notice all the factors that we have in this denominator. X and 2 times ln of x. I'm going to write the x before the ln of x. So that's a 2x. And I'm going to go back to write this ln of x to the 1/2 as a radical. And that's our final answer here. All right? So, well, we can use properties of logarithms to find the derivative of more complicated logarithmic functions. Well, let's see. Number 1, how about we review those properties? So, we might remember. Well, actually, I think we reviewed these properties back at the beginning of the semester when we were doing the review chapter, and I think we touched base on logarithmic functions. So let's review them again. So the logarithm of a product is the sum of the logarithms. The logarithm of a quotient is the difference of the two logarithms, and the power rule for logarithms. Well. I remember if I call this the smackdown rule. And basketball rule. So when the power becomes, when the coefficient becomes the power, that's like doing basketball, but otherwise it's like smackdown. All right. Well, so how can we apply this to find derivatives of more complex logarithmic functions? So, let's see. Find the derivative of the following functions using the laws of logs to simplify first. Because, well, number 1, if you were to do the derivatives of these functions the old way, without using the properties of logarithms, this would have been y prime equals 1 over x plus 2, 3x minus 5, times the derivative with respect x of x plus 2 times 3x minus 5. Alright? That is the 1 over u times du dx. Alright, the first part is fine, it's already simplified, but do you really want to do a product rule here? I don't think you want to do that. So, that's why instead, we're going to take a minute, we're going to take some time to expand these logarithms and write this product of logarithms as a sum of two logarithms. In other words, ln of x plus 2 plus ln of 3x minus 5. And this is in this case following the product rule of logarithms. Whenever we have a logarithm, well, in general a log, but in this case it happens to be a natural log. The natural log of a product in the argument, that's the natural log of a plus the natural log of b. That's essentially what we're doing in this case. And check these two functions that we're about to differentiate. It's a lot simpler to take the derivative of ln of x plus 2 and the derivative of ln of 3x minus 5. So, well, let's find the derivative. Y prime equals 1 over the argument x plus 2 times the derivative with respect x of x plus 2 plus, for the second term, 1 over the argument 3x minus 5 times the derivative with respect x of 3x minus 5. Alright? Okay, well, for the first term, what's the derivative of x plus 2? That's just 1 times 1. Well, let me write down that 1 over x plus 2 times 1 plus 1 over 3x minus 5. What's the derivative of 3x minus 5? What is that? 3. Alright, so 1 times 1, that's 1, x plus 2, and 3 times 1, that's a 3x minus 5. And we can leave it like this. In this case, of course, you can combine like terms by multiplying numerators and denominators by the missing factors, so we can find a least common denominator and then put all the fractions together. But this answer is acceptable. Alright, let's have a look at number 2, exercise number 2. G of x equals ln of x plus 1 over the square root of x minus 2. Alright, if we were to do this using just the ln rule, okay, so g prime of x, no need to write this. Let me show you how bad would have been if we were to do it this way. So that's 1 over x plus 1 over the square root of x minus 2. That's it. That is 1 over the quantity inside of the parentheses, which in this case is the argument, and then that times the derivative with respect x of this argument x plus 1 over root of x minus 2. Alright, well, the first part is easy to simplify because we can just multiply by the reciprocal. That's fine. I mean, the issue would be having to deal with a quotient rule, which, I mean, it's doable. However, instead of having to deal with that quotient rule, which will take a good minute to go, instead of doing this, let's take advantage of properties of logarithms. In this case, which property of logarithms are we going to use? Well, we have a quotient inside of the argument of the logarithmic function. So let me write it down. ln of a over b, that's ln of a minus ln of the quantity b. So let's apply that rule to this quotient here. Alright, so that's equal, so we're not differentiating yet. So that's just ln of x plus 1 minus ln of the square root of x minus 2. Alright, so we're almost there. We're almost ready to differentiate ln of x, well, the whole function. Well, that'll be 1 over x plus 1 times the derivative of x plus 1. However, the second term we can simplify a bit further because, well, in this case, you don't want to do 1 over the square root of x minus 2 times the derivative with respect x of the square root of x minus 2, which is doable. It's fine. You will have to do a mini chain rule there, but that's going to become really, really big. And we don't want these radicals as well. Actually, we're going to avoid the radicals in this case. So instead, we're going to write this radical as a rational exponent. And then we're going to use the basketball smackdown rule for logarithms. Let me write down that rule. So that's whenever we have ln of a to the r, that's r ln of a. So essentially, the exponent becomes a coefficient, or in other cases, the coefficient becomes an exponent, depending on the needs. So in this case, we're going to have the exponent to be the coefficient. So this is g of x still. We're not differentiating yet. And check this out. The reason I mentioned we're not differentiating yet is because ln of x plus 1 minus 1/2 x minus 2. So let me indicate with an arrow here what we did. And the reason why I mentioned we're not differentiating is because having this coefficient in the front looks a lot like doing the general power rule when we differentiate, when we have the exponent in the front, but in this case notice we're not subtracting the 1 from the exponent. Alright, so I think we're ready to take the derivative of this. So number 1, that's g prime of x, that's 1 over x plus 1 times the derivative with respect x of the quantity x plus 1 minus 1/2 1 over x minus 2 times the derivative with respect x of x minus 2. So in this case I could have just skipped that ddx of x minus 2, but the reason why I'm showing all these details here, it's because so you can see the chain rule in action along with this differentiation rule for logarithmic functions. Yes?
Can I ask where the ln went on the rightmost?
Which one?
The rightmost ln.
Oh! Yes, it should be here. Alright? Thank you. Okay, so the derivative of x plus 1, that's just 1. So 1 over x plus 1 times 1 minus 1/2 the 1 over x minus 2 times the derivative of x minus 2, which is also 1. Okay, so the only thing we have to do here, well, 1 times 1 is just 1, that's 1 over x plus 2, x plus 1 rather, minus, we can just multiply across to x minus 2, and 1 times 1 in the numerator, and this is a good final answer. Again, depending on the needs, if you're asked to write this as a single quotient, just multiply numerators and denominators by those missing factors to come up with a least common denominator. But typically, these are acceptable answers. Question?
When you have the x minus 2 to the 1/2, why is it negative 1/2 ln x minus 2 but not to the negative 1/2? I think it's correct.
This one?
Yeah, I think it's subtract the exponent by 1.
Oh, because we're not taking a derivative in this case. We're using the power rule for logarithm. The power becomes a coefficient. So just yes, I know that. So that's what I'm stressing on. So do not confuse with taking the derivative, because yes, having this coefficient, this exponent to become a coefficient resembles a lot like taking the derivative using the general power rule. But again, what we're doing here is just using properties of logarithms. All right. So these are a couple of examples on how to take advantage of these properties of logarithms to take derivatives of more complicated functions by taking advantage of these properties. All right. Now think about this. Think about having to do this derivative using the limit definition. Remember that process, which was a bit painful depending on the function that we were working. No, you don't want to do the limit definition on this one. And even if we wanted to set it up as a limit definition, we don't have the tools yet to compute some of the limits involving logarithmic functions. We would need another more powerful tool called the L'Hopital's rule to compute some special limits. All right, so it's time to leave behind that limit definition. All right, so the first part of this section was about differentiating logarithmic functions. This second part is called logarithmic differentiation. So the names are slightly similar, but logarithmic differentiation, we use it to combined with implicit differentiation to take the derivative of even more complicated functions that actually do not contain logarithms. Like a very classical example is this one, to find the derivative of x to the x, that is a function raised to another function. And no, this one is not going to be y prime equals x times x to the x minus 1. No, it's not going to be like this, because the exponent it's no longer a constant like we did when differentiating this general power rule. So no, the exponent this time is variable. So alright, what are we going to do in this case? Well, so we're going to take the natural log on both sides, and we're going to treat this problem like an equation, because when we take the natural log on both sides, essentially we're dealing with implicit functions, and to differentiate implicit functions, well, we have to go through the same steps we went about implicit differentiation in the previous section. Alright, so once we differentiate implicitly, we solve the equation for y prime the same way we did back in the previous section, and well, there's something else that we have to do, some sort of a back substitution. Well, I guess the best way to see these steps is in action with some examples. So number one, we have y equals x to the x. So we need to take natural log on both sides. I'm going to leave some space. Take the natural log on both sides, and this is going to give us, well, ln of y. And the reason why we take natural log on both sides is, again, to take advantage of the power rule of logarithms. Again, the one that in the exponent becomes a coefficient of the natural log. Alright, so in this case, x will jump in the front of the natural log function. Again, we're not differentiating yet. We're not taking a derivative, even though it looks like it. We're using the power rule for logarithmic functions. Well, so that's equal to x, ln of x, and we have an implicit function ready to be differentiated. So number one, what's the derivative of ln of y? Think of differentiating ln of x. What's the derivative of ln of x?
1 over x.
So 1 over x, right? But in this case, ln of y would be 1 over y.
Divided by dx.
But in this case, because we are differentiating implicitly, this y, it's depending on x. So we're doing a mini chain rule to differentiate this function of y with respect to x. Now, x ln x. Any ideas on how to go about the derivative of that function?
Product rule.
Product rule, that's because we have a product of two functions, right? And let's recall the product rule again. So the product rule, u v prime equals u prime v plus v prime u. And how about we write down everything? So our u is x and our v equals ln x. The derivative of u prime, is the derivative of x, which is simply 1. And the derivative of v prime, is the derivative of ln of x. And again, that's just 1 over x. Alright, so we have everything we need to differentiate this product. And again, following the product rule, u prime v, that is 1 times ln x, plus v prime, which is 1 over x times u, so that's 1 over x times x. Okay, let me label everything so you can see the product, the product rule in action. That's u prime v prime u. So that's the product rule in action on the right hand side of this equation. Well, so let's simplify some stuff in here. And let's see. So 1 over y dy dx, let's just leave it like that. 1 over y dy dx equals 1 times ln x, which is just ln of x. And see how the x's cancel out over here. That's plus 1. Alright? Again, when it comes to differentiating implicitly, our goal is to isolate the dy dx term, because, well, that's what we are solving for. That's what we're trying to find. So dy dx gets isolated by multiplying both sides by y. Alright, cancel them here. And this will be equal to y times ln x plus 1. So we are essentially done with the calculus. In fact, we're done differentiating the function. However, what do we have here? We have a function of two variables.
We replace the value x raised power x.
Alright, so we need to go back, substitute. Why? Because we know y explicitly, right? From the beginning of the exercise. So, in other words, y equals x to the x corresponds to this y right here. And this is dy dx equals x to the x ln of x plus 1. And that's our final answer. So that's how we differentiate a function raised to a power who is another function. Again, when you see something like this, y equals x to the x, y prime is not going to be x times x to the x minus 1. No, because the power in this case is variable. It's no longer, it's no longer a constant. That only works when we have something like y equals x to the 7. Well, in this case, y 7x to the 7 minus 1, 7x to this. It works only when the exponent is constant. Okay? We wanted to make this distinction. All right. Let's have a look at another example involving power, the derivative of a function raised to a power that is another function. So in this case, we have y equals to sine x square root of x, raised to the square root of x. So the first thing we do is take the natural log on both sides. Let me rewrite the function first. I'm going to leave a space for natural logs here. Sine of x raised to the square root of x. So let's take ln to both sides. And this, again, to take advantage of the power rule of logarithms, ln of a to the r, which is r ln of a. In other words, in a logarithm, the power becomes a coefficient or the coefficient becomes a power. That depends on the need in the situation. Well, so in this case, what we're going to do is have this power to become the coefficient of the natural log function. Alright, so this is ln of y equals square root of x ln of sine of x. And well, we're almost ready to differentiate this function, except that we have this radical here. We cannot just differentiate the radical as is. And again, we're gonna use the product rule because, well, we have the product of the function, the product between the square root of x and natural log of sine x. So ln of y equals x to the 1/2 ln of sine of x. And again, let me write everything on the side for this product. So recall, number one, that the product rule is u v prime. That's u prime v plus v prime u. Okay? So, and in this case, well, u is x to the 1/2 and v equals ln of sine. Okay? Alright. So let's do one thing at a time and then we put it together using the product rule. So, okay, the derivative of x to the 1/2, number one, u prime is 1/2 x to the negative 1/2, which is the same as 1 over 2 x to the 1/2, which again, back to radical, that's 1 over 2 root of x. Okay? So that's the first part. The second part, the derivative of natural log of sine. Okay, again, the derivative of a natural log, v prime, it's 1 over whatever is inside of the parentheses of the natural log function, which is sine x, times the derivative. What's the derivative of sine? Cosine, right? Well, in this case we can multiply cosine times 1, and then, well, we can simplify, and my advice is to simplify this. What's cosine over sine? I think we did it before, isn't it? Cotangent of x. So we have all the parts that we need for the product rule. So these 4 parts. Okay, so let's see. So let's go back to the original problem. Well, what's the derivative of ln of y again? The derivative of ln of y is? What was that?
1 over y.
1 over y? Just 1 over y?
Times dy.
Times dy dx. Again, that's because we're differentiating implicitly. Alright, well, we can go about the product rule u prime v. So u prime is the 1 over 2 square root of x times v, which is ln of sine x, plus v prime u, where v prime is this cotangent of x, times u, which is x to the 1/2. But in this case, since we're not going to differentiate this x to the 1/2, we can just write it back as the square root of x. And we're essentially done with the differentiation. All we need to do is multiply both sides of this equation by y. That's to isolate the dy dx. dy dx equals to, in this case, y that multiplies all this madness here, 1 over 2 root of x, ln of sine x times root of x cotangent of x. So we're done with the differentiation, we're done with the solving. All we have to do is go back and substitute for y, because we, in this case, we know y as an explicit function of x. If we didn't know it, well, we could leave it like this, but it's not the case. So in this case, dy dx equals the original function, and let me highlight it because y is all this function. Replace it here. So that's sine of x raised to the square root of x times all this madness here, 1 over 2 root of x ln of sine plus the square root of x cotangent of x. And that's final answer for this derivative. And again, we're taking advantage of logarithms on both sides. We combine it with implicit differentiation, and then this is our, right? This is our result. Okay, can we get anything even more complicated than this? Well, let's have a look at our last example. So, what about taking the derivative of this function? The y equals x to the 3/4 times the square root of x squared plus 1 divided by e to the secant of x times 3x plus 2 to the 5th power. Well, if you were to use the derivative the usual way, that'll be y prime equals 1 over this madness, you know, this whole madness, times the derivative with respect x of all this madness. I mean, do you feel like differentiating that quotient? So, this quotient that we have, well, actually, I think this combines pretty much every single differentiation rule that we have learned so far. We would have to use a quotient rule combined with products and chain rules, and well, you don't want to do that, right? What we're going to do is take advantage of properties of logarithms, same way. Notice in this case it's not a function raised to another function. In this case it's just some complicated function. So take ln to both sides. So take ln And number 1, we're going to use the quotient rule of natural logs. So ln of y equals, okay, ln of the numerator, x to the 3/4 times square root of x squared plus 1 minus ln of e to the secant x times 3x plus 2 raised to the 5th power. Now, each individual term contains a product. So we're going to use the product rule for logarithms twice, once for this term and once for this second term. So we're not differentiating yet, we're doing some algebra first. That's ln of x to the 3/4 plus ln of x squared plus 1, and I'm going to do something here. I'm going to change this to the 1/2 power, because then we're going to use another rule here. And then minus ln minus ln of e to the secant x plus ln of 3x plus 2 to the 5th power. Alright, this minus will affect the sign of the two terms whose product became an addition. So let's do a couple of things first. So number 1, let's do the power rule for logarithms a few times. Number 1, this 3/4 becomes a coefficient, this 1/2 becomes a coefficient, this 5 on the exponent becomes a coefficient, and recall how ln and e are inverse functions of one another, so we can cancel those. And well, ln of y equals 3/4 ln of x plus 1/2 ln of x squared plus 1, and minus simply secant of x, and minus, because the minus affects the sign of both terms inside of the brackets, so minus 5 ln of 3x plus 2. Alright? And at this point, I think we're ready to differentiate this function. Well, so again, the derivative of ln of y, that's 1 over y times dy dx equals 3/4 times the derivative of ln x, which is simply 1 over x, plus 1/2 the derivative of ln of x squared plus 1. And well, in this case, the derivative of x, so that's going to be 1 over the argument, which is x squared plus 1, times the derivative of the denominator here. What's the derivative of x squared plus 1? 2x, minus the derivative of the secant function. And does anybody recall the derivative of secant? I think we did that. Secant tangent. And minus 5 times the derivative of ln of 3x plus 2, 1 over 3x plus 2, times the derivative of 3x plus 2, which is just 3. Alright? So let's simplify this. So this will be 1 over y dy dx equals 3 over 4x. And notice how these 2's cancel here. And we can multiply x times 1, multiply that across to get x over x squared plus 1 minus secant tangent, and minus 5 times 3, which is 15, 3 over 3x plus 2. So we're done with the differentiation. All we need is to move that y to both sides. I mean to the other side. So that's dy. dx. Well, I'm going to leave some space over here so I don't have to write the whole thing. So that's 3 over 4x plus x over x squared plus 1 minus secant tangent minus 15 over 3x plus 2. Technically, we should multiply by y over here, but to avoid writing again this whole madness, I'm just going to go back and write the original function x to the 3/4 square root of x squared plus 1 divided by e to the secant x times 3x plus 2 to the 5th power. And this is final answer. So the question is, would you expect something like this on the exam? Yes, a very common exam questions. It's to differentiate a function like this that contains this madness. You have to take advantage of all these properties of logarithms. But ultimately, we do all this to find the derivative of simpler functions, right? Instead of having to differentiate that quotient that contains products and chains at the same time.